Hello, am I audible? Hello,
Yes, sir, you are audible.
audible, right? Okay. Uh, okay. Can you tell me like how many of you are having that ROE session for BDM today?
8 p.m.
Okay, how many of you are having? Can you just raise your hands? Seven. Okay, 7 8 people. Okay, fine. Uh, okay, fine. So today actually, I think next week you are having exam, right? Quiz two. So uh, we have to finish week eight along with solve with us by today, right? I hope you understand. Okay, so actually, week eight is not very difficult week. Actually, if you see, have you watched the lectures for week eight? All? Okay,
No, sir.
Few videos,
not yet.
not all. Few
Not
videos.
all. Okay, fine. See, we are going to see theory. Along with that, we can finish the problems from solving the slides. So this week I will not do one thing. Maybe I will not, give you time to solve those problems, since we do not have much of the time left, right? So what we can do is I will solve the problems for you, right, from week eight. Is that fine?
Yes, sir.
Okay. Okay. Fine.
Sir, solve with us for week 8 and
Yes.
week 7, right?
Huh? Week seven is done, right? Not
Week 7 is done. Okay.
on
No,
that
sir.
day. Huh? When
In week 7, the PC question are very confusing. Also in graders and
from the graded assignment also. Huh?
yes,
But
yes,
I
sir.
think the session has happened, right? I think on Thursday the session was there.
Actually,
Okay.
when we try to see the solution, then we have different ways to solve. This is the confusion. Like
There is one.
somewhere,
Yeah, yeah. But there is one PDF which is there from the Solve with Us slides. Is it shared with you? If it is not, I'll share that with you. Yeah. So there are two questions given in there. One is for I think it is for yeah, so the matrix was I think it is 2 by 2 or 2 by 3 or something like that. I don't remember it exactly, but there are two questions, and I have given the steps like how to solve that. If you follow only those steps, you don't need to worry about others, right? Anyway, I'll share that slides with you. Along with that, what we can do is whenever we have another session, right, in the revision session, I will try and show you how to solve that. Is that okay?
okay, okay, sir.
Yeah.
Okay, okay. Thank you, sir.
Yeah, so maybe one session will take this week. In that, we will solve about week seven as well. Is that fine? Okay. Okay, so this week is about solving the unconstrained optimization. So, have you heard optimization problem previously? What is that optimization problem? Any idea? Anyone? No idea.
Optimizer means like finding the extreme values. No?
Okay, have you encountered sorry, have you encountered any you know concept of optimization previously?
Yes, sir. In the max too, like Sanidhi sir told a bit
Okay, yeah, right. And uh,
about
okay,
optimization.
correct, correct. So there are two types of optimizations, and this is see this optimization concept is very important. Once you learned the machine learning, right? So in machine learning, optimization is the very important concept. You will see those concepts in MLT also. But yeah, before that, we'll try to learn what are these concepts, right? So this week is fairly easy compared to the next week. We have okay in optimization we have two types of techniques. Maybe I'll just show you those techniques. Okay. Yeah. I hope my screen is visible to you. So let us say this optimization, right? So there are two types. One is the constrained optimization and another is unconstrained one. So this week is about unconstrained optimization, right? What do you mean by unconstrained and what is the structure of optimization problem? I'll try to write it down for you. The problem is of minimization or maximization, right? So basically it is these two problems we'll try to solve: maximizing any function given the constraint or minimizing any function given the constraint. That is our constraint optimization problem. So basic structure of this problem will be like this. So it is kind of you can say that it is minimum, right? So let's say min of, right? So any f of x, I will write down the terminology which is used there, right? And then we'll see that what exactly is there. I think all of you have solved these kind of problems from your high school time, or not high school, at least in 11th and 12th. Fine. So but you might not know whether we call it as optimization problem or not, right? Okay. So this is the basic structure of the problem, which is, let's say, minimizing this function, right? Or maximizing. So here let us consider minimizing the function over this x, right? So x will be in what? In r dimensions, right? Okay. So x is a data set, let's say, and or any function which is in r d dimensions, and we wanted to minimize this given the constraints. Let's say g of x is less than or equal to 0 for all, let's say, okay, I'll say that, okay, there are multiple constraints. For example, these constraints are like this: gi of x is greater than 0 for I, all I equals to 1 to k, and hi of x is equal to 0, hg of x. J of x will be equal to 0 for all j from 1 to k. What does this mean? Uh, okay, I'll try to tell you what is this exactly. This is your, this function is called as the objective function. Okay, this is called as the objective function.
Sir,
Uh,
one,
yeah, yeah, yeah.
sir, when you write x belongs to RD
Hmm.
below the min,
Hmm.
that means we need to find not the minimum value of the function, but the
Minimum
minimum
value
value.
of the function in d dimensions, right? So I'll tell you the example of it, and then we'll discuss about it. Is that
Okay.
fine?
Okay.
So basically that x is the, so let's say I'll try to say that, let's say the minimum value of the function comes out to be x star. Fine, right? Some value will be there, right? But that value should be in d dimensions. uh, Let us say, because if let's say your function is f of x is x square, so this x, right? So if I wanted to find its minimum value, what should be its minimum value? And generally, how you solve this problem? F of x is equals to x square. What do you do to find its minimum value? You find out its first derivative and equate it to 0, right? Correct. And then from there, this x star will be your critical point, and then you find, then you do the second derivative, and in that you see that whether the second derivative is greater than 0. If that is the case, then x star equal to 0 will be what? The minimum value of that function. Is that fine? This is the flow of solving the minima problem, right? Or minimization problem. Is that correct? I hope this simple problem all of you know. You have a function which is x square, which is a function of x, which is x square here. I need to find out its minimum value. The first step is to find out its first derivative and equate it to 0. If I equate it to 0, what I'll get the critical point, right? And then you find out its second derivative of this function. So or the derivative of it, right? So derivative of a derivative, you'll get which is the value should be 2, right? And if it is 2, in this case it is 2. If it is greater than 0, the function will have what? Minima.
Minimum.
If it is less than 0, we say that it is the function will have maxima. And see, let us say in this case we are getting some value, right? But suppose you get some 2x. Okay, maybe I'll just scroll it. Suppose your function is like this: f of x is x cube. Is that fine? uh, okay, I think x cube will not have the minima, right? Basically, okay, maybe I'll, but f dash of x will be, okay, what is f dash of x here? 3x
3x.
square, right? And if you equate it to 0, what should I, what I'll get? X is equal to
Yeah.
0, right? Actually we'll get 2 points, but both are both of them are 0 0, right? And f double dash of x will be what? 6x, correct? Now this value is not exactly greater than 0 or equal to 0. What you will have to do is, whatever value you have got from here, these are the critical points, you will plug in those critical points in here. And if I plug in those points here, what I'll get here? So 6 into 0, right? And that gives me 0. So when you get 0, that will be what? The saddle
Saddle.
point, right? So what I wanted to convey here to you is, when you have when you get the critical points, right? And when you take the second derivative, you'll have to plug in those critical points into that derivative. So when you think about this problem, which is what, f of x equal to x square, in that case you don't get so this value, right, 2, it is free from x, correct? It is not having any value where I should plug in that 0, right? Because x is, there is no variable, it is free from that variable. And now you got this 2, which is greater than 0. In that case I can say that it is a minima. So whatever the problem this was, this is called as an unconstrained optimization problem. But coming back to your question, where you said this x belongs to Rd, right? So now in this case, if I try to draw a graph, what this graph will look like? So this will be your x-axis, y-axis will be f of x, right?
Pointing up.
Right, and the graph of, when I plot the graph of x square, it will look like this, right? And it will pass through the origin, which is 0, right? Or I can say it is 0 0. Fine, is that correct? Right. So but here if you think about this x is in which dimension? Can you tell me, like, is it in r2, r3, r or only
R, sir.
r, right?
R.
Because you are changing the values of x along only x-axis, right? Only on one direction. So that is this is a real line, and your x is in r now, and this x star, whatever you got, what is x star here is, which is 0. It's a minima, right? Right. So this x star equal to 0. This is in what? R, right?
Yes.
So what I'm trying to say is, when your x, right, the variable which is going inside your function, right? If it is in Rd, the minimum value of that function will also be in that dimension, right? Rd. Is that correct?
Yes, sir.
Now you got it. So when you solve this problem, f of x equal to x square, that x was there, that x was in R, and so that the minimum value of that function, which is 0, that also is in R. Okay, fine. So this is a general structure of, or general form of a optimization problem, right? That we try to solve. There are several techniques to solve this optimization problem. Uh, I will see those techniques maybe in this class. Some of the techniques we'll see, and the next session or next week, which is week 9, in that also we'll see few of the techniques, right? So before that, this f of x is what? This is your, this is called as the objective function,
Objective.
right? And these two, these are the constraints. These are called as constraints. Okay, sorry. These are your constraints. right? So now this constraint gi of x, which is less than or equal to 0, and hj of x, which is equal to 0, what is the difference between these two constraints?
One is equality, another is inequality.
Right. So this is like, these constraints are the where you have so this function, whichever whatever is written here, is exactly equal to 0, and the other one, right, which is less than or equal to 0, that is the difference between these two constraint. So this constraint is called as what? Is called as the inequality constraint. Inequality constraint.
Sir, one small
Yes,
clarification, sir.
yes, yes.
Will it always be just two constraints, or can it be anything?
See, not two, right? So when I say I equal to 1 to k and j equal to I to L, there will be so many constraints, right? Maybe it
Okay.
will be one, or it will be more than that, or it will be two, it will be five, it will be 10.
So it
But
doesn't necessarily have to be less than zero. It can be greater. It can be anything.
yeah, it can be anything, or it cannot be, like, you do not have the constraint. If you don't have constraint, what will happen then? That problem will become
No.
unconstrained optimization, right?
Got it.
This was the unconstrained optimization, because I asked you to find out the minimum value of this function, but there was no constraint over there, right? Now what I'm trying to say is, if you have the constraint optimization problem, it will have, let's say, five, in your problem you have five constraints, right? But the nature of those constraints will be only these two. So there will be only two types of constraint possible. Which are those? One is inequality, and another one is equality, right? Understood? This part is fine.
So what are those G and H? Why did we choose
Some
like that?
functions, same functions, because see here I have written a f of x, right? So these are also
Okay, okay.
some kind of functions. Okay, maybe I'll try to write down some, like, this was the general form, right? So maybe I'll try to write down some.
Can you show some examples?
Yeah, yeah. So so this actually constraint optimization problem will solve it in the uh, next week. But I think one of the example which was given in the lectures, right, by professor, it was this one. Suppose I think minimum of, let's say, I'm taking that same example. I think if you have seen that first lecture or second lecture, it was there. Uh, so it's this row x1 minus 40 squares plus x2 minus, let's say how much, then 40 square. This is what? This is your objective function, right? This is your objective function. Which one is objective function here? X1 minus 40 square plus x2 minus 40 square, right? So that is your objective function. Here your, let's say, if your x is this vector x1 x2, can you tell me this x is in which dimensions?
R2, sir.
R2, right? Okay. Now let's say there is one constraint which is like this, x1 minus 20 square. So generally this problem will, it will be written like this, st. What is it? St
Such
such
that
that, right? So such that x1 minus 20 square plus x2 minus 30 square, which is less than or equal to 10 square, and let's say there is x1 which is less than or equal to 25. So this is the problem which you wanted to solve, right? And this is called as a constraint optimization problem. So can you tell me, this is also one of the functions, right? This is a function of x1 x2. What about this? This is a function of x1 only. Right. So I'm just right, since that my general form is like that, I'll say that this is my f of x, which is the objective function. This first constraint I'll call it as g of x, and the second constraint I'll call it as h of x. Is that fine? Is that okay?
yeah.
Issues? Any issues there? No, right? So you can, sorry, okay, I'll not say h of x, maybe it is g1 of x and g2 of x. Why I'll say g1 of x and g2 of x? because both of them are the inequality constants, right? So it's kind of it's a method of writing it, right? Like if you wanted to see that general form, uh, I wanted to relate it to that, the same general form, but it need not be like g1 of x. The important meaning of this is, okay, I'll try to another way, is basically this is a function of, let's say, g1 of x1 x2, right? Is a function of x1 and x2. And what about this g2 of x? G is to show that it is a inequality constant, and h is some equality constant. This is only the analogy. It doesn't require to be g only. I can write anything else, maybe f of x, f1 of x, f2 of x. That doesn't change the meaning of it, right? Okay, this fine. Any doubts still here? Hmm?
Sir,
Hmm.
this constraints depends on the behavior of the function. If the,
No, no, no.
um,
No. It is not like that. See, let's say it depends on what are the requirements of yours, right? So, for example, if you are working in a manufacturing industry, right, and you wanted to, let's say, or any industry you are working in at, and uh, suppose you are actually manufacturing a product, fine, and the cost of manufacturing that product, right? If let's say it depends on two factors, uh, I don't know, let's say there are two factors which are there, and let's say one of the factors is defined by x1 and another factor is defined by x2, fine. Now these two factors, right, I wanted to minimize the cost of the product, fine. So let us say how much cost you can reduce, right? That is your objective function. And okay, see the product, right? The product cost depends only on these two factors, which is, let's say, x1 and x2. So how much cost cutting or whatever you wanted to do, it depends on only that x1 and x2. But uh, the manager of yours said the x1 the quantity of x1, let's say, cannot be lesser than some threshold, fine. Let's say in this case it is x1 is less than or equal to 25, so x1 cannot exceed more than 25, fine, correct. So that is the constraint, right? So that's, let's say, that might be a natural constraint, or that might be a constraint provided by, let's say, whatever your manager is there, or maybe if you are working with some other companies, right? So they said that this is our constraint, that you shouldn't use that product more than this quantity, or that product shouldn't use less than this quantity, right? So that kind of constraints will be there. It is not like it is mandatory or something like that. If it is not required, you don't need those constraints. So it is not like every time you have to solve the problem with the constraint. uh, I hope you understand. If you are not understand that also, that is fine. See, the thing is, in data science it will be a different task to do, right? So there will be some constraint which are naturally occurring, or there will be the constraint because of some assumptions you are doing, right? So you, let's say if you try to solve some algorithm, and in that algorithm there is a constraint of, let's say, whatever the distribution you are using, it is a normal distribution. So because of that, the constraints might occur over there, fine. So those constraints might be the natural constraints, or it will be the constraints which are uh, there because of the assumptions, fine. We'll see about those anyway. Maybe in the next week we'll see some problems over the constraint optimization. But see, it is not needed to have the constraint optimization problem every time. Okay, so I'll tell you one of the examples of unconstrained optimization. Let's say, again, I'm taking it from the lectures itself. uh, we'll see, when we are solving some problems from solve with us, we can see more questions on this as well. Okay, so let's say minimize, I wanted to minimize this, x belongs to R, and suppose this is x minus 5 square. X minus 5 whole square, right? Okay, how will you solve this problem? So what is the objective function here?
x minus 5 is square
The whole
minimized.
square, right? So I need to minimize this. So I'll say that f of x is equal to x minus 5 whole square.
You have to find the minimum value.
Yes, minimum value at which this function gives me the minimum value of x such that this function will give me the minima of this, right? So yeah. So how will you solve this problem?
First derivative,
Right. So you'll find out its first derivative, and what is its first derivative?
2 times x plus x minus 5
Right. And what you do then?
Equal
equals
to
to
You equate it to 0. So
x equal
from
to
there,
5.
I'll get a critical point. And what is it?
5.
X equal to 5.
5. Right. Okay. Okay. And this is your minima, right? But okay, again, you'll have to check whether that is minima or not. But
Second derivative,
yeah, but let's say if I don't,
Um,
if I know that this is going to be minima, right? Let's say, uh, basically you do what is to, let's say, take the second derivative. And what will be the second derivative of this?
2.
2.
2, 2, right? So because it is 2 into x minus 10, so this will become 2x minus 10. And if I want to take a derivative, it will be 2 only, right? Yeah. Okay. So this is greater than 0, and in that case, I will decide that this is going to be a minima. Okay. So the minimum value of the function occurs at 5. So what is the minimum value? X star. Let's say I'll call this as our uh, minimum value x star, which is equals to 5. In this case, I'll say that this is going to be 5. So this is the easiest problem, right? Easiest problem of the unconstrained optimization. So this is one of the techniques, from calculus, that you take the first derivative, equate it to 0, and then try to find out its minima. But there are some limitation to the technique, and if you have this kind of limitations, I'll need to know the is there any other way to solve that problem, right? So can you tell me about this problem, which is 3x to the power 6 plus 2x to the power 5 plus 3x cube. Again, this is again same example from lectures, so I'm not doing anything else here. But what is the problem with this problem? Can you tell me how will you solve this? You'll take its first derivative, right? What is this first derivative?
18x to the power 5
Hmm?
plus 10x to the power 4
Hmm?
plus 9x square
Hmm?
plus 10x
Right, and equate it to 0.
0.
Can you tell me what are the values of x?
One will be 0 and another we'll have to solve for it.
Right. So is this easiest now to solve this polynomial?
No.
Right. So that means if you have the polynomial function, right, as your objective function, even the unconstrained optimization problem solving is not that easy, right? Okay, is that correct now? I hope this is fine. Right. No,
Yes.
so there is a limitation. So do you have any other way to solve this kind of problems, right? So there is another way, which is called as a there is uh, another algorithm, which is the iterative algorithm. What do you mean by iterative? That means you go it's stepwise and try to reach that minimum value. Suppose in the case of y equal to x square, or f of x equal to x square, so there is a function f of x which is equals to x square, and that is this function, right? So let's say this is your objective function f of x equal to x square, right? uh, I'm saying that you start randomly with some point. Okay, so let's say I started with this point, and in one step I will move towards the minimum value. Fine, I will reach it here after one step, and I'll take some more steps, and I'll try to reach to the minimum value. So somebody will say that I will start somewhere randomly. Let's say I started with this point, and I will reach here from like to the minimum value. Okay, so this is possible by iterative algorithms. Like, and what kind of algorithms they are? So there is one algorithm which is called as the gradient descent algorithm. But before reaching to that algorithm, right, try to understand that uh, how we can say that that algorithm will exist. Fine. So maybe you can actually it is possible that you can study with yourself, but for this right now, can you tell me that if I start with this point, what does that mean if I started with this point? Or okay, maybe let us say I'll draw one more graph. Or sorry, I'll do one thing. I'll take this example, x minus 5 whole square. This is fine. I can take y equal to x square. Or yes, any doubts?
Oh, what's the question?
Okay, I'll tell you the question. So this is the function, right? Y equal to, or maybe f of x. F of x equal to x minus 5 to the whole square. So what is the graph of this? Generally, we know for this kind of simple equations, right? It is possible to draw a graph. Let's say this graph will be this, because I know that since I know this, there is a minimum value here, and the minimum value is at what point? Is at x equal to 5, right? Right. So I said that to you, there is an iterative algorithm. Let's say, and what are you doing in that iterative algorithm? I will start with the some random x, right? Start with arbitrary x, fine, or x naught, let's say, which belongs to R in this case. Just give me a minute. Okay, I started with arbitrary x, which is in R, right? Fine. So that x naught can be this side, right, or it can be this side. Is that correct? It can be uh, towards the left of 5 or towards the right of 5. So this is my first step, to start with some random x naught. Now what I'll do is I will go from iterations, and iterations means, let's say, steps, right? I'll go from 1 to 2, let's say t number of steps, and in that steps what will happen, I will update my x t plus 1, right, by x naught, or let's say xt plus some d. Okay, we'll try to understand what is it. So let's say if I start with this x naught, so what is the corresponding value of the function here? This one,
f of x naught.
right? So this is, let's say, it is f of x naught. So by looking at this graph, my where is my minima? It is at 5, right? So when I start with this, where should I? And okay, at minimum point, that is x equal to 5, what is the value of the function?
0.
0. That's right. So now if I started with this x naught, which is towards the left of my 5, what should I do? Should I choose the values which are left of x naught or which are right of x naught? Which direction should I go?
Right of x naught.
Right of x naught, right? So I should choose the direction which is right of x naught, right?
Sir,
So
how
yes,
do we know which direction to go and without
that is correct. That is correct. But let's say for understanding purpose, I know this graph, right?
Okay, sir.
Okay, we'll reach to that part where we'll see that we are automatically with this gradient descent algorithm, we are automatically choosing the right direction. Fine. But for now, what do you think? If I start with this x naught, right, which is a random x naught, which is on this x along that x-axis, if I started with this x naught, where should I move ideally? Towards the uh,
Right side, positive
right
side.
side, right? So towards the positive side, right? Okay, and let's say if I choose this x naught, where should I move towards?
X
Towards
naught
Left side.
minus.
right. Okay. And what I said is, let's say after x naught, I chosen this value. Let's say this is x1. Okay, this is my first step. In the first step, I have chosen x1, or I have moved to x1, right? So I moved to this step, let's say, and uh, let's say this is my direction. So what I'm saying is, after x naught, x t of 0 plus 1 equal to x naught plus d. So I moved by the distance d, right? So let's say this is the distance d, or direction d, whatever you wanted to prefer, that is fine. So am I going correctly towards my 5, right? So choosing this x1 is good idea here. Yes, right?
Right, right.
Right. And now if I wanted to, let's say this is why this was my first step. After that, I'll move towards x2 and like that. And my hope is that I will end up at 5, right? Which is the minimum value of the function. Okay. So again, the question arises that, okay, how do I know that this is the right direction, and how should I keep a tab of it, right? So that is correct. That is one question. There is another question that, again, uh, so to answer to that question, can you tell me what will happen to the function's value? So this is f of x1, right? So can you tell me f of x naught is greater than f of x1 or less than f of x1?
Greater than f of x1.
Greater than f of x1. So if I want, so my objective is to find the minimum value of the function. In that case, if I take a step uh, in the right direction, in this case, when I started with x naught, if I take a step in the right direction, what should it happen? The function's value should be decreasing, right? Right.
Yes, sir.
And okay, that is correct, right? So what does that mean is, if I am at, so my x naught is less than 5, right? In this case, x naught was less than 5, right? In that case, the function's value at x naught should be less than or greater than f of x1 if I choose the direction d. Let's say if I choose the direction d, or the distance d, which is what?
To the right of
Just
x1.
So to the
To
so
the
it
right
will,
of x1.
yeah, so it will be lesser than or greater than? Greater than, right?
Greater than 0.
Greater than 0, right? Because I'm going from here to here. So at that time, the direction which I'm choosing, right, it should be greater than 0. Okay, that's fine.
Right, sir. One doubt. I
Yeah.
think in week 5 we did the similar kind of problem. One problem was given
Hmm.
that this gradient descent function. I mean, the loss function was implanted in the gradient descent, and
Hmm.
uh, wherever this loss function is
Decreasing.
achieving, yeah, decreasing the lowest.
Yeah.
And so one doubt is, like, we try to achieve to the max minimum of the loss function.
Hmm.
What should be the target for the this algorithm? Should you always try to get the trend of the algorithm, like minimum or maximum, how it should be?
No, so our hope is to get the minimum of the function, right? So and that also has to be done into what, finite number of steps, right? It shouldn't be like, okay, you will be reaching to the minimum at infinite number of steps, right? It should be some finite step, let's say 1000, 100, 10, 15, 20, like that. So our hope is to get to the minimum of the function. Fine.
But then, how do we know how many iterations we have to do?
Yes, that is, see, all of that doubts are correct, but let us see, like I'll tell you, like at the end of, once we get that algorithm, right, you will get to know whether we'll reach to the algorithm's minimum, or where should we cut it off. Fine. So basically, there is a topic of convex functions. Maybe it will come to the later part of, I think, week 9. Uh, but yeah, before that, I'll try to like I'll try to let you know, like, how will you get that, or whether always will get the minimum of the function, right? That is also the concern, right? I'll tell you. Don't worry about it. Like once this discussion will end, right? I think most of your questions will be clear. Fine. Okay. So, sorry. Okay. Suppose this was again. I am writing the same function. Sorry for my diagram. Yeah. Yeah. Let us say this is again 5, right? If I started with x naught here, which is the right of my 5, the which direction should I choose? Greater than 0 or less than 0? Less than 0. And what that will achieve, let's say this was my function at x naught, and suppose this is x1. Again, can you tell me, is it giving me the same thing which was there when I started with this x naught, right?
Yes.
So can I say that now I'll summarize everything. So this x naught, if my x naught was the arbitrary value, right? So if it is greater than 5, right? The direction should I choose to move will be less than 0, right? Correct? And if my x naught is less than 5, the direction which I should choose to move should be greater than 0, and both of them are actually achieving me this part, right? So my function's value is decreasing if I do like this. Is that correct?
Sir, when you say d is less than 0, you mean left? No, sir.
Yeah. So d is less than 0 means uh, I should be, so this is x1, right? So let's say it was x1 here, x naught here. I'm saying that d is less than 0. What does that mean? It's uh, negative addition. So what was our iterative algorithm? I think I have written it here, right? So this is the update rule. What was the update rule? Xt plus 1 should be equal to xt plus the d. What is xt plus 1? The next step, right? From the previous step. Xt is the previous step and xt plus 1 is the next step. So suppose in this case, what is your first step? I have started with x naught, right? Is my arbitrary value or random value which I have chosen. After that, what should I do? What will be x1?
X naught plus.
X naught plus some d, right? So let's say my x naught is here, so that d should be, was what I'm saying is negative, right? So that will become this one, right? X naught minus t, right? So I need to subtract something from this x naught so that I'll reach to this 5, right? Correct? Uh,
Got it, sir. Yes.
right. And what about this part? If my x naught is on this side, I should add something to this x naught so that I'll reach it to 5. Okay. I hope there are no issues now in this case. Okay. But like again, the thing is what? How do you decide the d, right? So the direction where I need to move, how should I decide that, or whether it is a function of something or not, that I need to understand. So can you tell me how? So let's say if x naught is here, then I need to say, I am saying that if x naught is less than 5, then d should be greater than 0, and if x naught is greater than 5, then I'm saying that d is less than 0. Can I say that this direction is a function of x, right? So what I'm saying is it depends on x, right? Is it correct? Is that fine? Because where I'm choosing this x, based on that I should choose my direction, right? So definitely this direction should be a function of x, or maybe you can say that it might be dependent on x, right? So this direction d is dependent on x. Is that okay?
Yes, sir.
So if x decreases, then the direction will be negative. Like x0 to x1 it is discontinuous.
Where is that x, right? So the location of x actually is important in deciding whether I should add something into that d. Let's say, see, in this case I am adding x naught plus d when x naught is less than 5, right? So if it is on the left of 5, and when I'll do that, I'll subtract that d when x naught is greater than 5. So that means this direction, right? Whether I should add or subtract, it is depending on the value of x. Okay, the value of x has be is the key here. To, because see, if x naught is greater than 5, should I move to this side? If I say okay, I'll just take this rule only into the uh, uh, consideration. Suppose, and suppose this is my, so I'm saying that when whatever x is there, I don't care. Suppose x naught is here, what I'll do is I'll add something to it. So that, let's say d is some value, I'm adding that value into this x naught. So I'll just go with this this update rule, that xt plus 1 should be equal to xt plus d. In that case, so now if I add some d into this x naught, what will happen? Where should I'll go? I'll go towards this side, right? But my goal is to not to uh, go somewhere that side, right? I should go into this side. This is the correct direction to move in, right? So if I wanted to move towards this, then that means I need to subtract some value from this x naught, so that I can, in finite number of steps, I'll reach it to this minimum value of the function, right? But in this case, let's say if I started with this x naught, okay, when I'm saying that, when I'm started with this x naught and that x naught, how I am doing that? Or since, why it is happening? Because it is a random thing, right? You are randomly choosing that x naught from the all the real values. So I'm saying that you pick any real value, and now you start with that, it will eventually end up to the minima. It should end up to the minima. But again, when I pick it randomly, right? So it might be that it is possible that this value which I'm picking it randomly, it will be uh, on the left of the minimum value or right of the minimum value. So I need to choose a correct direction to move in, so that I will reach to the minimum value. That's the goal here. Fine. So in this case, let's say what was my function? It was the function of x minus 5 whole square, right? Fine. And suppose your x is greater than 5. I'm saying that x is greater than 5 means where is my x naught? Here, right? This side. Correct? Hmm?
Yes, sir.
Okay. So in this case, what is f dash of x? It is 2
2
times
times x minus
x minus 5. And if it is x is greater than 5, so let's say x is greater than 5, which value? Let's say I picked the value 7. So what will be the value of f dash of x in this case? F dash of x will be
4.
4, right? Right. So it is greater than 0, right? uh, I hope you understand this part, right? So now what I'm saying, so you understand that, right? Like if dash of x is greater than 0, that means the slope at this point, right, at the function. So let's say x naught is 7. So suppose this is equal to 7, the function's value is at here, and when I take a slope, it will be like this, right? Something like positive slope or something, right? I don't know whether this drawing is correct or not, but suppose this is a slope. So that means I should be descending over the slope, right? I should be coming down. And if I wanted to come down, uh, in this case, what should I do here? Should I subtract something from 7, or should I add something into 7 so that I'll reach to the minimum?
Subtracting.
I'll have to subtract it, right? Yes, correct. And suppose my x naught was equal to x naught was equal to, let's say, 3, correct? So in that case, f of x is, let's say again, x minus 5 square, and this x naught is 3 is less than 5 or greater than 5? Less than 5. Then f dash of x, or f dash of x at x equal to 3, it will be what? 2 of x minus 5. So it will be negative value, right? Minus 4 is a negative value. So what I'm trying to say is that when okay, so when I'm less than 5, the direction should be, so I need to add something into this, right? Is that correct? I need to add something here, and when I'm greater than 5, I need to subtract something from there. So can I be able to take or find some rule or some direction such that if I take that direction as it is, I'll be able to achieve uh, both the things simultaneously, right? So in that case, I'm saying that it should be like this. So I am assuming that this direction is equal to minus of f dash of x. Okay. So what was the update rule previously? I said, what was the rule? X t plus 1 equal to x t plus d, right? That was the rule,
Yes, sir. This was the
right? So now I'm choosing d equal to minus of x. So what will be the rule now? X t
minus
Minus
of
f dash x.
f dash of x. Okay, so this is the updated rule right now. Okay, can you tell me this will work for any choice of x naught, whether it is towards the left of it or towards the right of it?
Yes, sir.
Should it work?
Yes, sir. Definitely.
Right? Because if your x naught is less than 5, in that case, f dash of x value is less than 0, right?
Yes, sir. Then we'll add.
And it will get added, right? So then it will become xt plus f dash of x, right? So it will be adding. And when x naught is greater than 5, then f dash of x was greater than 0. If you can see it from here, we have seen that, right? So in that case, it will get subtracted, and that is what we needed, right? So when I'm right side of the 5, I should subtract that value, right? So I should be 7 minus let's say 4. So it will give me 3. So I'm actually going towards the left of x naught. And if you have x naught equal to 3, then that minus of minus will become plus, and I'll be adding that to here. I hope so. This rule is working, right? This rule is working, right? Yes or no?
Sir.
Sir,
Yes, sir.
Yes, yes.
sir, just adding f dash of x will work, no? Like,
No, if I add f dash of x, what will happen? Let's say if I say that xt plus 1 equal to xt plus f dash of x, right? Right? And now let's say what was for f of x? F of x was x minus 5 square, correct, right? And suppose your x is greater than 5. Let's say I took x not equal to 7, right? What is the f dash of x? Okay, f dash of x is common, which is 2 times x minus 5. So f dash of 7 is how much? 4, right? 2 times 7 minus 5 is
I
4, right?
think maybe the inside the square thing is confusing, but we are right to say it is minus f dash of x.
So let's say it is 7. If I do plus, and I'll have to add 4, right? So I'm getting 11. But that means I'm going away from 5, right? But my intention is to go nearer to 5, because 5 is the minimum point, right? But understand the problem with this adding f dash of x.
yes, sir.
Yes, sir.
Yeah. So this is my updated rule. But so that means I'm done or not, right? So I need to check that whether I'm done or not with this part. Uh, there is some problem with this. Let's say, what is the problem? Okay. Suppose this same example I'll take. So what is my function now? F of x equal to x minus 5 whole square. This is my direction, which is, let's say, minus f dash of x. But for now, I'll just take it like f dash of x. What is f dash of x? 2 times x minus 5, and now this is my update rule, which is xt plus 1 equal to xt minus f dash of x. Is that okay? Is fine. So now I start with random value of 7. Fine. X naught of 7. So what is the f dash of x or f dash of 7? It is equal to plus 4, right?
Yes,
Na?
yes.
So x1 will be equal to x1 equal to uh, x is
7 minus 4.
x naught, right?
Sorry,
So it is
7.
7
7
minus
minus 4.
4, which is equal to 3. Okay, so that means yes, I'm right, actually moving towards my left. Okay, now my x1 is 3, right? Okay, so next step is what? To check whether the function's value is decreasing or not, right? So initially the function's value at 7, what was it? It was 7 minus 5, which
4.
is 2 and 4, right? Okay, now what is happening at 3? It is again coming as 4, right? So that is again, I know that now this is also not the minimum value, right? What should I do now? I'll have to go
Again,
for,
iterate.
yeah. So what is the f dash of 3? Minus 4.
Minus 4.
Now x2 will be, sorry, x2, the second iteration will be 3 minus of minus 4, which is again 7. So in the next step, what will happen? Again, I'll go back to 3, right?
Yes, yes.
Right. So what is happening here? What is the problem we are facing here? Is that I'm actually hopping between these two values only, right? I'm going from 7 to 3. I'm going from 3 to 7, and it will happen again and again for so many, like infinite number of steps, right? So even though the direction which we have chosen is the correct, the direction, what was the direction we have chosen? Minus f dash of x. This looks correct, but the problem occurred with this direction is that I'm actually not be able to go to the or nearer to the minima, right? So can we do one more thing in this case? Uh, okay, what do you think? What is the solution to this problem? Let's say, okay, I'll just draw the diagram once more, right? So this is my 5. I was at 7 initially, then I moved to where? 3, right? So I went from 7 to 3, and then again I went from 3 to 7, and in the next step also I'm doing like this. So what, can you tell me what should be the solution to this? The direction is correct, because yeah, whenever I am on the left side of the 5, I am going to the right side. Whenever I am on the right side of the 5, then I'm going into the left side. That is correct. What is the solution to this?
Means
Maybe no. Maybe the way we are moving here is actually one step, right? Like we are taking entire full one step. Is it possible that if I take a smaller step, right? So if I do like this, let's say if I just do, I don't hop from 7 to 3 entirely. Instead of that, what I'll do is I will take the, let's say, half of the step. What does that mean again? Again, let's say if I say that something like this, xt plus 1 equals to xt, sorry, not plus, minus minus 0.5 of 0.5 of f dash of x, right? Does it solve the problem for me? Can you tell me, like, what will happen now? 7 minus 0.5 of f dash of 7. What was that? 4?
So in this case, it will move from only one direction, right, sir? It will not hop both sides. Is it that correct?
No, no,
Is
it
that
will
correct?
hop. It will hop, but it will hop in a different way. I'll tell you how. Okay, maybe I'll take the that another example, like, because here we have already reached the minima. But take, let's say, instead of 7, we take maybe we started with 10, right? So some more large from this. What will happen in that case? And I am saying that I am moving only 0.5. I'll take the half step, right? Instead of taking the full step, I'm taking the half step. Whether I okay, not half also. Let's say I'll take some more bigger. Okay, this also works. Let's say 7 also will work. Fine. What will happen in this case now? Some fraction of the step I moved, which is 0.7 times 4, and 7 minus 0.7 times 4 is how much?
4.2.
2.8. And what will be the value?
4.2.
Sorry,
4.2.
Yes, right. So we okay, from here now we have reached to, we didn't reach to 3, we reached to let's say it is 4, and here it is, we have reached somewhere here, right? So from here I reached to here. Is that fine? Previously I used to go from here to here. Now actually I am moving closer to this. What will be the next value then? X2 value. So now I need to find of x dash of 4.2, and what is it? 2 into x minus 5, which is how
Minus
much?
1.6.
Minus 1.6. Right. So in that case, x2 will be, so this was x1, x2 will be 4.2 minus 0.7 times 1.6. So that will become plus. So 1.12.
5.2.
So it is 5.32. Right. So from here I'll reach to here somewhere. Let's say this is 6 here, 5.32, right? Somewhere here, correct? So I'm just moving from here to here. Is it okay? So now what we are actually doing is we are, so what was the distance between 4.2 and 5? So initially the distance was 5 to 7. What was the distance? It was 2 step away, right? Or 2 away, right? 2 units away from, so 7 was 2 units away from 5. Then from 2 to where we have reached, 5 to 4.2, how much it was? It was 0.8, right? And now 5.32 is how much away? 5.32. So what we are doing actually, we are inching closer towards the minimum value. Is that correct? I hope this is fine. So the direction we chosen was the correct. The only problem was that I was actually taking the full step, right? And that's why I was hopping between these two values. So instead of that, we are actually taking the smaller steps. And if you take even smaller steps, maybe you'll reach it to the 5 faster. Suppose instead of uh, 0.7, I took 0.6. What will happen? This will become 2.4, and this value will become 4 point, how much? 4.6,
4.6.
right? 4.6, and then the next value will become what? Like this is 4.6, and then this will become 0.6. I think okay, this value also will change accordingly, and I think it is 0.8 minus 0.8, right? Minus 0.8. So this is 0.48, and now this will become 5.08, right? 5.08. So now if I take the more number of smaller steps, I'll be actually reaching to the solution faster, right? Compared to the large number of steps. Is that correct? Right? I hope you understand this part clearly. So as you take the smaller number of steps, there is a hope that you might converge faster to the solution. So this is called as a convergence step, right? So we might be able to converge faster. So now the updated rule will be what? Xt plus 1 equal to xt minus eta t of what?
D.
F dash of xt. D is basically your minus f dash of x, right? So this is my updated rule. Fine. And this eta t, I'm writing it as, it might be a, so this is called as a step size. So how much step size I'm taking in each iteration is step size, and this might be a constant, or this might be a this might be the function of t. Function of t means function of the iterations. Is that okay? So I'll give you one example of this step sizes. Whether so previous in the previous question, the example I have taken. Yeah.
Excuse me, sir.
Yes.
Sir, yeah. Sir, will eta t be a constant? Because since if it's a function of t, it will vary, right?
Yeah. So it might be constant. So I'm saying that it is not necessary that it should. It is see, eta t is a hyperparameter actually. Okay, maybe you guys might not know that word, but it's kind of like that. It is a choice of individuals, right? So it is your choice what eta you should choose. So you can choose as a constant, or you can choose it as a function of the step function of the steps, right? Or maybe the iterations. So let me tell you. So it is a scalar quantity anyway. So let's say this is a function. It can be like this: 1 upon t to the power 2 to the power t, and my t will be, or I can choose eta t as like 1 upon, let's say, t plus 1, right? Or I can choose eta as some constant, 0.5 or 0.6, that we have seen in the previous problem, right? So it is up to you which eta you wanted to choose. So you wanted it to diminish as your iterations, because see, what we have seen is, if you have the smaller eta, what will happen, or smaller step size, what will happen? There is a chance that you will uh, you will converge it, right? So your solution will converge it faster compared to the larger eta. Okay. So among these three, which is better? Let's say, okay, leave about this part. What do you think? This is better or this is better?
Second one is
Yeah, and t will start from 0 to infinity, yeah? Or 0 to infinity, let's say, and here also 0 to. So why second? Okay, this is first and this is second. Second one you are saying better. Why you are saying it is better?
because the first one basically converges to a certain value. Right?
Yeah. So if I take a summation of all, right, summation of all step sizes, so the summation of this uh, t equal to 0 to infinity 1 upon 2 to the power t, basically what are these values? So in the first iteration it will be 1 upon 2, right? Or okay, or maybe 1, where 2 to the power 0 is 1. The second iteration it will become, if I put 1 here, it will become half, then it will become 1/4, it will become 1/8. So what is happening here? It is basically decreasing. So this step size is decreasing after each iteration. This looks like a good one, but if you take the sum of all, right, that sum actually, uh, if I limit it to this, right, so it will limit to some 2, because if I take sum of it, it is 1 plus half plus 1/4 plus 1 8 or 1 8 1 by 8, or like this. And this is basically a geometric uh, distribution, right? Or sorry, geometric progression. So if I take so what is the r here? Half, right? Half, right? And in this case, what will be the summation? So when r is less than 1, the summation will be like this: 1 upon uh,
1 minus r per n.
1 minus
R
Minus r.
r, right? And that
or
will,
r equals
yeah,
infinity.
that is my sum, right? So it is 1 upon 1 minus half. So this will become 1 upon
2.
half, and this will become 2. So that means the summation will be so this is the finite value. And in this case, what will happen? So the first value of it will be at t equal to 0, the value is
1.
1, t equal to 1, the value is half, t equal to 2, value is 1/3, 1 by 3, numerical 1 by 4, 1 by 5, and like that. In this case, there is not geometric progression, right? So there is this will actually, if I take a sum of all of these step sizes, right, it will sum to the infinity. So what is the understanding from here is that it is better to choose that step size uh, which will converge what to finite value, or which will converge to the infinite value.
Infinite, sir.
Yeah, because when it will converge to the infinite value, that means it will not stop at one point. What will happen to this step size? The problem with this step size is that uh, after one point, right, there is no uh, decrement, right? So after one point, it will be useless to go forward with these step sizes. So those step sizes, it will go to or it will converge to the infinity. That will be the best step sizes are there, right?
These step sizes, like we can take, like, differs from different problem to problem, right?
Yeah. So that is what said. No, I said like it is a it depends on this is kind of a hyperparameter, right? So it depends on what problem you are solving and what is your need. So you can actually use the custom step sizes also. It's not mandatory. Maybe once you see some machine learning problems, right? Maybe when you take that MLP course, you will be better able to understand that because see, whatever problem we are solving here or we are seeing here, they are like it's a 2D problems, right, which we wanted to visualize, but it's better to see in a like larger data set. In that case, it will be like very less or it will be like better to visualize in that. But yeah, the step size is like it is a choice of a person who wants to take it at. But what is the idea here? When you wanted to choose a step size, whether it should be greater than 1 or less than 1, it should be less than 1, right? Yeah. And whether the value of the step size is lower is good or the higher is good.
Lower, sir.
Lower is good, right? So because then it will not actually it so in this case, you saw right, when we took zero point 0.7, the hopping here was reduced than this, but still it was there. So 4.2 and 5.32, right? But when I had the smaller eta, in that case we were actually hopping around like very nearer to the minima. So that is also one of the reasons.
Sir, but say for example, in case in this case, we are minimizing the objective function,
Yeah.
right?
Yeah.
But say for example, in some case, we are maximizing the objective function.
Hmm.
So in that case, probably the step size, if the step size is larger, then it would be good, right?
See, the thing is, maximization problem. This will the gradient. It will not be the gradient descent rule. It will be a gradient ascent rule.
SN rule, okay.
Okay, and in that case, the direction so it will be like this: eta f dash of x t, fine,
Mhm.
right? Or maybe eta t. Again, you are ascending into that, right? So the problem will be like this, right? The convex function,
Right, right,
concave
right.
function.
Concave
Again,
function.
so again you have that the
Ah,
for eta it will be the same thing, right? Again, you're understanding. So it will again be between the 0 to 1 because you don't want the very high eta. What will happen,
otherwise, it will again cross.
Yeah,
Okay,
you will
okay.
cross here, again it will cross here, and it will like that. It will happen like this. So it will not reach here. With the higher step sizes, it is definitive possibility that it will be like uh, it will not reach to the objective value, right?
Okay, it will keep oscillating
Yes,
basically. It will never
yes.
come.
So when you have the low, right, what will happen is maybe in the first step you will reach here, like smaller step you will take, and eventually you will reach to that value, right? But this is a gradient ascent rule, and this is a gradient descent rule. So whatever problem you are solving is a minimization problem, and in that it is a gradient descent rule. But idea is same in both the cases, right? Yes. Okay, so eta t, and it is f dash of xt. Okay, fine. Okay, now this is for we have seen for this when x was in real numbers. Let's say x is in RD. What will happen then? This gradient descent rule will look like what? X t minus eta t will be del f of x t, right? Okay, but xt plus 1 is a vector, right? Is a vector in RD. Is that correct? Similarly, xt also is a vector in RD. Here it is x is in t plus RD, right? Yeah. And this will be also in, right? Is that okay? Eta t anyway is a scalar. So this is a scalar and this will remain R and R. I hope you understand this problem or this algorithm. Right?
Right, sir.
Okay. So now one more issue I'll say that, or one more thing we want to discuss. So I think I have given you one problem, right, initially, and that's why we started with the discussion that should we have any other algorithm than merely by solving it using the calculus, and that problem was this: 3x to the power 6 plus 2x to the power 5 plus 3x cube plus 5x square by plus 2, something like this, right? So can you tell me what how this graph will look like? I don't know, or maybe you might also not know, but might this will be a polynomial, right? Something like this, correct? Is that okay? Is in x.
Yes.
So where is the minima here in this for this function? Where is the minima?
Right.
Last.
Here, right? This is my actually x star, right? X star of this function. In this iterative algorithm or gradient descent algorithm, what is our first step?
Pick a random point, sir.
Take a random point, right? So suppose if I take a random point here and use that iterative algorithm, is it possible that I will reach it to this x star with the gradient descent algorithm?
Yes, yes,
Yes. If I take a point here, should I reach it to here?
yes.
Yes. But let's say if I pick a point here, will I reach it to here or will I reach it to somewhere else?
So you'll reach it to the
Here is
last minimum. The
Here, right?
Next minima.
Here,
Yes.
right?
Yes.
So what is the understanding of this? This is what is called as the global minima, right? It's a global minima. That means it is a minimum uh, of this polynomial, right? Exact actual minimum of this polynomial, and these are all what? So this also one minima, this also one minima, this also one minima, this also one minima. These are all called as the local minima. So with the gradient descent algorithm, uh, so do you understand that whether we will reach it to the local minima or global minima, it depends on what? Where we initialize, right? Is that correct?
Yes, sir.
Yeah.
Yes.
So uh, depending on the random, since we are taking a random initialization, it does not guarantee every time that we will reach to the global minima. What this algorithm guarantees you is that you will reach it to
Local
the
min.
local minima. So that is a drawback in this case, I'll say. But most of the problems which we encounter into this data science, right? Uh, we don't have to worry about it because there is a good set of functions which are called convex functions. Maybe we'll talk about it in the next week. Uh, the property of convex function is that they have the whatever the local minima they are having, that is exactly equal to the global minima. So now one case, okay, one thing is that what this is my gradient descent algorithm, which is xt plus 1. Okay, you choose x naught at random. So this is a random initialization. This is my first step, and then you iterate over the t steps, and in that case, you'll say that it is xt plus 1, xt minus eta del f dash of xt. or del f of xt, sorry, not x dash. Del f is what? The gradient, right? Gradient, right? Fine. So these are the major topics in your week 8. Shall we try and solve some problems over this?
And then how it is helping in optimization?
Yeah, but at least you are reaching it to some minima, right? See, optimization is what, like your point in optimization is to what, to get the minima or the maximum of the function, right? That is the optimization thing. Uh, Gradient descent will not guarantee you that for every function it will give you the global minima, but it will guarantee you that you will reach it to the local minima. So most of the problems it will be useful anyway, because without see, if even if I'm not getting the global minima, I'm there is a chance that I'll be getting the local minima in a finite number of steps, and if it is possible, then we can use that information to do other tasks. One more thing is, most of the problems, or not most of the problems, but like yeah, the problems which are encountered into the data science field, right, they are or the functions which we are evaluating, they are the convex functions. And the properties of convex function is that one of the properties of it is that it will reach it to the global minima. So the gradient descent algorithm will give you the global minima, because the convex functions will have only one minima, that is a global minima. So in that case there is no local minima. For example, your f of x equal to x square, right? That function is a convex function. Fine. F of x equal to the x, I think x to the power 4, I think it even though it will have two minima, both of them are actually the same, right? So there are functions which are called as convex functions. They have the global minima only, so that way
So
it will be useful anyway. Yes.
in case it is not a convex function, but even though it will give a kind of understanding that which direction it has to take a move, and when it reaches to the local minima,
Yeah.
maybe it is not the perfect solution, but we know we are close to the solution, like some
Correct.
direction towards that. Yeah.
Correct. Correct. Yes. Yes. Right. So we are like, it is not that bad, right? In this case also, if you think, it's not that bad. Instead of ending up somewhere else, it is not that bad compared to this. So that is the idea here. I think I have left one more topic. Maybe I'll finish that and then we can solve some problems. Right. So yeah, there is one thing which is,
Sir,
yeah.
uh, how do we know when to stop using, like, when will it converge? How do we know which point will converge at?
So okay, how do you, first of all, first question is, how do you know that whether you are going into the correct direction? What I said to you, if you remember it, it
That
is like,
f of x need to be minimum,
right?
lesser than the earlier. Yeah.
Yeah, right. So f of x1 should be less than the f of x0, right? And f of x1 should be greater than f of x2, like that, right? So every time you move forward, if it is, if you are getting a lesser value, right, lesser functions value, that means you are doing it correctly. If such thing happens, right, like let's say f of x1 is less than f of x2, what does that mean? This is going to be your minima, right? Understand? One more thing is that if you are getting the same values, suppose f of x1 equal to f of x2, again if you go for further, f of x3 is also same, that means there is no further decrements possible. In that case also, will stop, right? So these are the criteria to where to stop. Is it fine?
Got it, sir.
And sir, in reality, that whether all the time we will come to know how would be the loss function, and if we know the loss function, and if it is not really complex one, we can still know what is the minimum for
Yes.
that loss function.
Yeah. Yeah.
Okay.
But in that case, you don't need anyway that iterative algorithm, right? Because if loss function is like this, right? So square root loss function, I think most of you, if you know that linear regression is a thing, right? So it is y minus x square, right? Basically, or y minus wx square, right? So that loss function is actually a convex function. So do you need the iterative algorithm there, right? When you need in that case is that your data, right, it is very large. In that case you need it, otherwise you get the solution easily. I think we have seen that using the least square method, right? We have solved it using linear algebra technique also. So that is also one of the techniques. So if you have that kind of equations, you don't need this algorithm. Basically, you can solve it using the calculus or by the linear algebra, right? Okay. Yeah, I see. I think, see, all of you, whatever the questions you are having, right? Most of will get addressed into MLT, and more like remaining will be get addressed into MLP, because all of these techniques which you are learning, you will see the use cases in there, and that will be that way. It will be like connecting all the dots. Right here, we are just learning the basics of calculus optimization, like that. Where to use it, we haven't seen yet. Correct?
Sir, are we going to do the solve with us today?
Yeah, we'll finish it off now. Like few questions are there. I will solve those questions. Fine.
We need to complete it before 8, right, sir?
Yeah. Otherwise, if you are okay, I can take it tomorrow. That session, uh, like maybe 1.5 hours. Because I think some of you are having that class later on at 8 o'clock. I'll There is only this topic remaining. Maybe I'll stop at here, and maybe from 7 to 8 or 8:30 we'll do it tomorrow. Is that okay?
Yes, sir.
Tomorrow, day after, right?
Yes.
I think the deadline to submit VCAT is Tuesday, right?
Yes.
So if you guys are fine, we can take the solve with us tomorrow.
So Tuesday, like this Tuesday or next?
This one. Oh, next one, your quiz will be there, right? Your
Oh,
quiz will
yes, sir.
be ending up.
Exam will be over,
Yeah,
sir, by then.
yeah.
Yeah.
So
29th is the revision.
I think he's forgetting that quiz 2 is
yeah,
coming.
quiz two is in the Sunday. You will have to do that. So
No, I remember about quiz 2. I was a bit
uh,
skeptical about the GA submission.
Okay.
no, 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 no. Week 8 is deadline this Tuesday, and see, I will take one. If you want, I'll take one session tomorrow, maybe 1.5 hours,
Yeah, tomorrow,
and
if you can take, sir, it's better actually.
okay, fine, I can do. And let's say if I get the time right, and if you are fine with that, I will cover week 7. I think if you guys have some issues with that PCA steps, right? Uh, Maybe I'll cover that also tomorrow.
Sir,
That's fine for me.
regarding week 7, sir, I have one confusion is there. Sir, the last lecture that is there in week 7, in
Hmm.
which he talks about PCA for higher dimensions. When the dimension, the RD is greater than the number of points that we have.
Correct.
Sir, could you give a quick explanation for that, sir? I have issue in that.
So actually, okay, it is there in MLT. Again, we are actually learning that in MLT very rigorously. But I'll tell you what is it exactly. So basically, what are you doing here in PCA? So you know, right? So there are some, let's say, bunch of data points, right?
Yes, sir.
Here, and now you wanted to extract some information, or you, let's say, this is called as a dimensional reduction technique, but actually it is not reducing anything else, right? It is just doing that one thing. What is it called? The linear combination of the data points, basically. But okay, I think all of that is not there in this week, but the core idea is what you what you do generally, you find out the eigen direction, right? Sorry, is that correct? So let's say these are the data points x1, x2, x3, and x4. What do? You try to project that data point onto some direction, right? Let's say the projection is here. Is that correct?
Yes, sir.
Right? And now you are saying that this is some error after projection, right? Let's say this E1, this E2, this E3, and this A4, right? This projection will be what? Let's say if this direction is W, the projection over here is W transpose X1. This is W transpose X3 like that, right? And what is the vector here in this case? If I multiply it with W, is that correct? What is W in this case? It's eigenvector. Or I don't know. I think you guys have used U, right? U is U transpose something. Is it correct? Uh, I'm, I hope all of you know this part. If you are confused with this, then I think a lot
No,
of
sir.
this is fine,
Sir,
right?
yeah, so this normal PCI I understood, sir, but in
Correct.
PCI in higher dimension, sir.
Yeah, yeah, I will tell you. But do you understand this part?
Yes,
What,
sir.
so you are projecting all the data points onto a eigenvector of all that data points, right? So basically, what you
Yes,
do,
sir.
you find out the covariance matrix, you find out its eigenvectors, and you project all the all data points onto that eigenvector, right?
Yes, sir.
PCA in higher dimensions basically is that is your x1, right? Okay, okay. There are two ways actually to understand that part. So in this case, what you are getting is you are getting a linear combination of all data points, right? In x1, x2, even that x1 is in R2 or x1 is in R3, doesn't matter. But what is the, or let's say x1, x or not x, xi is all the data points in, let's say RD. Uh, we are able to project all of that onto a line, right? Why it is possible here? Because there is a linear structure associated with here, right, along the data points. Is that fine? You're understanding that part? So as my x1 is increasing, or as my uh, or I can say that all these data points inherently are lying onto that line, right? Okay, I think if you're not understanding this, okay,
Sir, in the lecture, sir, they mentioned something about it is
kernel.
enough to find the eigenvectors of 1 by n A transpose.
Oh, okay, okay, that is the case. Okay,
That is my question,
that
sir.
is fine. I understand. Okay, that is also fine. That is also not an issue. Okay, so generally, what you do here in this case, you find out the covariance matrix, right? What is the covariance matrix?
1 by n summation
Or okay, let's say okay, you tell me,
x
then I'll
I
tell you.
minus
Yeah,
summation
summation of
xi minus
uh, xi
xv
minus x bar
x bar
and
into xi minus x bar transpose.
transpose, right? Right. So basically, you are doing what here? You are doing the centralization of the data, right? Is that fine?
Yes, sir.
Suppose your x bar is 0, right? So that means all the points, right, data points actually, uh, or you are understanding the centralization.
Yes, sir. Got it, sir. This is a covariance matrix.
Yeah.
But sir, the procedure to do PC in higher dimensions, sir.
Yeah.
Sir, in the lecture videos, they clearly explain how to do PCA normally.
Uh,
But in higher dimensions, sir, what is the procedure regarding 1 by n A into A transpose? What is
I'll
the
tell you. Yeah, so everything is there in MLT. Anyway, you'll understand it better in there. But I'll try to showcase you in this case here. So in terms of let's say your x bar is 0, right? That means the mean vector is 0 of all data points. It will look like this: xi uh, xi into xi transpose, right? Is that correct?
Yes, sir.
In a matrix form, how does it look like? 1 upon n xx transpose,
Yes, sir.
right? This is my covariance matrix. And what you do later on, you find its eigenvalues and eigenvectors, right?
Yes, sir.
Correct. So what will be the eigenvalues of, let's say these are the eigenvalues lambda 1, lambda 2, and let's say lambda n eigenvalues you are having for this matrix. And the corresponding eigenvectors are, let's say, what do you take? Maybe beta 1, beta 2, and let's say beta n. These are the eigenvectors of this matrix, right? Is that okay?
Yes, sir.
This is also matrix, right? X transpose is a matrix.
Yes.
It's a symmetric matrix, right? Anyway, covariance matrix symmetric. If I take this n this side, what will happen? This will become nc, right? nc is equal to x transpose. Is that fine? Is that okay? No issues there? Hmm?
Yes, sir. Sir, sir, if possible, could you please um, go to the dashboard, sir? The
I'll tell
left.
you. I'll tell you. No, I understand your point. I will tell you there. I'm taking you to there. If you just understand this, you will understand that part also. Okay, just 2 minutes. It will not take much time. What are the eigenvalues of this matrix? Can you tell me? If the eigenvalues of this C is this and eigenvectors are this, what do you think the eigenvalues of X transpose matrix are?
I think same
No,
eigen.
n times, right? N times lambda 1, n times lambda 2, and n times lambda. Is that fine?
Okay, sir.
Because the eigenvalues of matrix C are this. See, if you have if A is having eigenvectors lambda 1 and lambda 2, what are the eigenvectors of eigenvalues of 2A? 2 lambda 1 and 2 lambda 2, right? Like this, it is n lambda 1 because n times C. But what about eigenvectors? They will not change. They will be same, right? Because this is the eigen equation, right? A lambda equals to let's say beta lambda, fine, or lambda times beta, whatever, lambda times beta or whatever you want. If I think if you know that from X, but I'll say since I have used beta here, I'm saying that beta is the eigenvector. So what is the eigenvector of 2a lambda or 2a vector? So it is 2a lambda, then 2 lambda beta. So here your eigenvalue become 2 lambda, and the vector will remain the same, right?
Sir, it is A beta, no? A
Huh?
beta is equal to lambda beta.
Sorry, yeah, a beta is sorry, a beta is ax1, yeah, correct. A beta equals to lambda beta, and then what is 2a beta? It is 2 lambda beta. The only thing changing here is eigenvalues multiplied by 2, but the eigenvector remains the same. Is that correct? This from eigen equation. Now can you tell me what are the, if you know that the eigenvalues of a transpose and a transpose a are the same, correct?
Yes, sir.
Right. So can I, what will be the eigenvalues of a transpose, or in this case x transpose x?
It is a dot product, sir.
No, eigenvalues.
What is this X?
Eigenvalues remain the same, right?
Yes,
Yes, sir.
should
Yes.
be same.
And lambda n, right? But will the eigenvectors remain same for this?
No,
No, right?
it will change.
Actually, the eigenvalues also will not be equal to n lambda n, or more than that. But since if I talk about A is a n cross n matrix, right? In that case only this will be the same. But let's say if it is a rectangular matrix,
Then
A
there
is a
might be an
D
additional
cross
zero.
n, right? D cross n matrix. In that case, what will be the dimension of A transpose?
D cross D.
D cross D. And what about A transpose A? N
N
cross
cross
n.
N.
And let's say if D is greater than n, D is much larger than n, what will happen?
First, the non-zero eigenvectors will be shared, will be same, and the remaining will be zero.
Right? So the eigenvalues here are actually as remaining as the same. But what about this? The eigenvectors. Let's say the eigenvectors of this are alpha 1, right? Alpha 1, alpha 2 to alpha n. So this alpha 1 is equal to beta 1? No, right? But there is some relation between these two. Basically, beta 1 is equal to alpha 1 upon root of n lambda 1. Okay, so if you divide it by root of n lambda 1, you will get the eigenvector of this. So it is
Is it is it the singular value sort of a thing?
yes, correct.
What is this alpha?
Alpha is the eigenvector corresponding to this matrix X transpose X.
Eigenvector.
Ah. Uh, okay, it's okay. I think, see, if I'm explaining it in like 5 minutes, it will take but much. Uh, if you understand it, like if you understand PCA properly, right, you will understand it better. But no issues
So
with that.
regarding, sir, could you please go to the dashboard one, sir? That
Okay.
would be very helpful.
Uh, or do you want me to?
Sir, yes, sir. Lecture PPTs.
Okay, I'll do that PPTs, right? So I think it is need from week 7, right?
Week 7, sir. The last lecture, sir.
Where this one?
Yes, sir.
Okay, it's visible.
Sir, can you zoom out a little?
Ah, this fine, right?
Yes, sir.
Ah.
Yes, sir. Sir, in this, sir, if they give a problem regarding PCA and higher dimensions, basically we just have to do it normally. There is no change.
Yeah, we don't give the problems on this actually, not much of the problems, but yeah, see, that is what I tried to explain it to you, that the eigenvalues of A transpose and A transpose, they are the same. I think it is mentioned, it is like that only, right?
Yes, sir.
So instead of solving for A transpose, you can solve for A transpose A, and again the procedure is procedure is same, right?
Okay, sir. Sir, the last statement, sir, in the last slide, could you
Ah.
please explain that one, sir?
So instead of working with the D by D matrix to find X eigenvalue, it is enough to find the eigenvalue. Yeah, that is what I tried to say, tell you right here. So when your D is larger, what will happen?
Oh, got it, sir. Got it, sir. So instead
You
of
don't.
doing A
Yeah,
transpose A,
yeah. Instead of solving for 1 upon n, let's say X transpose, right? This is your covariance matrix, right? Instead of solving the eigenvectors for this matrix, solve it for X transpose X, because this will be your D cross D matrix and this is going to be your N cross N matrix. And when D is much larger than N, so suppose
right,
your D is, let's say, 1000 feature vectors, right? And number of examples are 50, right?
right.
In that case, solving for this 1000 cross 1000 matrix, it's better to solve for 50 cross 50 matrix,
Got it, sir. Got it.
because the eigenvalues of both this, right,
Both of these will be same.
same. The eigenvectors are not same, but if you divide the eigenvectors of this matrix by this quantity, you will get that eigenvector, right?
Okay, sir. Sir, could you once go back to the slides, sir, please?
Okay. Yeah.
Sir, so here, sir, I didn't understand A also. How is A the same C? So covariance matrix is equal to 1 by n A transpose A.
Yeah.
So A, sir, could you just once explain
A
what?
is a data matrix, like all this vector. This is A, right? X1 minus X bar, X2 minus X bar. This is a matrix, right? This is
Okay,
so you okay. This A is nothing but, okay. I think the notation has given, so many notations are there. But let's say what was your data? X1 was given something, right? Right. This is your
yes,
problem in general. X1, X2, and X3, right?
right,
Now you find out it's X bar, right? Some value, and
yes,
then you do one thing, right? Is that X1 minus X bar 1 upon n, and you just multiply with uh, I think I doing it wrong. So let's say it will be a vector, right? Anyway,
yes, sir, got it.
so x1 minus x bar x1 minus x bar is this, right? Suppose I'll say that is x1 minus x bar, and you multiply with x1 minus x bar, right? And then you add like this, right? You do generally like this,
Yes, sir.
and this. So A is a matrix of this, all rows of, let's say, x1 minus x bar. or okay, in the rows, this thing. It's a
Okay.
vector vector, whatever the vector is there. You, maybe I'll just give you some example. Say 1 2 3. X2 is, let's say, 2 3 0, and x3 is 0 1 0. Fine. So what is mean vector here? 1 uh, 2
1.5.
1.
Okay.
Right? Correct? Hmm? Correct, right?
Yes, yes, correct.
Yeah.
Yes.
What is x1 minus x bar?
0, 0, 2,
0 0
2.
2. X2 minus x bar? uh, 1 1 minus 1, right?
Yes, sir.
And x3 minus x bar is minus 1 minus 1 minus 1, right? So now
Yes.
the matrix A is formed like this: 0 0 2 1 1 minus 1 minus 1 minus 1 minus 1, right? And the A transpose will be this: A transpose will be 0 0 2 1 1 minus 1 minus 1 minus 1 minus 1. And now what you do is you just multiply this with this A transpose divided by 1 upon n, and in this case it is 3. That is your covariance matrix C. But you are actually doing not using the matrices, you are solving it using like this: 1 upon n summation of xi minus
Okay, sir.
into xi minus x square. So what you are basically doing is you are taking this vector and taking its transpose, and you are multiplying it, right? So basically you are doing,
Same thing. Both of them are the same things, no,
that
sir?
is what, yeah, correct. It will do the same thing.
Yes, sir. Sir, one more thing. Could you please go back to the slides?
Hmm.
The
Sir, you'll be taking Taylor tomorrow, right?
Yeah, yeah. Okay, I'll take tomorrow Taylor also, and that solve the
Because
question.
time is already over.
Yeah, yeah, yeah. I need you guys need to go there. I'll take that tomorrow. What is this?
Sir, so sir, in normal PCA, will find the U1, U2, U3 based on the eigenvalues
Hmm.
of this covariance matrix
Correct.
and the eigenvectors of the covariance
Correct.
matrix.
Correct.
Here, how will we do? What is the procedure, sir?
Here also you take the eigenvalues. Actually, eigenvalues basically are same, right? For this A transpose A,
Right.
or A transpose whatever, right? It is same, right?
Right.
Now you, what you do is find out its eigenvalues, and I told you, right, this is the relation. We'll have to use that relation, but that is not in your syllabus, that
Then we can leave it. So, sir,
uh,
so in this whole lecture slide, just to understand, if we understand that box, it's enough, sir.
yeah, yeah, that's fine, because the scope of this PCA is not like too much. It's like content into the specific things. You will
Okay,
learn PCA in proper way in MLT. So there is one more
got it, sir.
kernel PCA is also there. So it is there. Once you enroll into that MLT part, right, and those who are already there, I think they understood it. But you, when you go into that MLT, you will understand this PCA very properly.
Okay, sir. So for this
This
MLF,
is enough. This is enough.
just understand that instead of
Yeah,
A transpose A, we have to do A
yeah,
transpose.
that's it.
That is more than enough for
Yeah,
this
yeah.
lecture.
You don't. Yeah, you don't need to solve for anything.
Okay, sir. Sir, one more small question, sir.
Yeah.
We with the first method, before max variance, the least error method,
Hmm.
and max variance method, both of them will give the same PC algorithm, no, sir? Just wanted to confirm.
What maximum variance? Okay, maximizing the variance, and yeah, this, okay. I think yeah. So meaning of that both is same. So
Sir, like in the second lecture, he explains we want to find the direction in which the variance is maximum,
correct.
right? So the final PCA algorithm from max variance, the lecturer derives it. So the maximum maximum variance method of PCA and the minimizing the error method of PCA, both of them will give the same algorithm. I
This
just
is,
want
yeah, this is the same algorithm. Actually, in both way, we are achieving that part. So okay, I'll tell you that. Maybe I'll just take your 2 minutes. Uh, if you So let's say you have this data set, right, and now this is your so how many lines can I draw it from this to so basically your algorithm is based on this, right? This is your error, right?
yes, sir. Minimizing error, and then we'll take the direction where the variance is maximum.
Right,
I
yeah, so this is the errors, right? You're projecting
right,
those errors, and there are like multiple lines you will project, and you will choose
right,
only that line which gives me the minimum error, right? So
right,
suppose this is the minimum error, right? The
right,
variance is this one. How far these values these projections are from each other.
right.
So this line which gives me the minimum error, right? That same line will give me the maximum variance. That is the understanding of this part.
Got it, sir. Got it. So both the methods will arrive at the
Not
same
both methods.
algorithm,
This is only one
find
method.
the
Yeah,
eigenvalues of covariance
correct.
matrix, and then
Yeah, yeah. So eigenvector is that direction which minimizes the error. Also,
okay,
it
sir.
minimizes the sorry, it maximizes the variance.
Yes, sir. Sir, one more small question, sir. Could you please go to the lecture slides?
Hmm.
Could you go to the first lecture, sir?
Hmm.
Yes, sir. Sir, could you go one slide down?
Yeah.
Sir, here in approximate xi in purple it is written, no, sir. Approximate xi by xi tilde as follows.
Hmm.
And they give an expression. Sir, here there are from u the number of unit orthonormal vectors are from 1 to d. So it's a d-dimensional vector, no, sir. So why here they're mentioning m-dimensional subspace?
Where it is written, okay, projected
Right
data
next to
point,
it,
okay,
the
that belongs to
sir,
the m dimensional subspace.
but it is a d-dimensional subspace,
Which
no,
one?
sir.
Which one? Xi tilde you are talking about, or bj uj?
Xi tilde, sir. The one below the purple line.
But belongs to a m dimensional subspace. Okay.
But it should be a d-dimensional subspace, no, sir. The
No.
professor kept mentioning it explicitly, but I'm not able to understand why is it.
Okay, I didn't see the lecture, so I need to. Okay.
Sir, leaving the session, sir. Thank you.
Okay.
So can you share questions of PC that you have mentioned before?
Yeah, I'll share that with you. Maybe tomorrow's lecture I'll share that with you. Right? Tomorrow's session or maybe I'll attach to this calendar also. That's fine.
Okay, okay, thank you.
Yeah. Mm, approximate xi by xi tilde as follows. Uh, okay, projected data point belongs to a m dimensional subspace. So D is your what? And what is M here? What? Xi is in RD. Project D onto m dimension. Right, no. It's correct, right? But the this point, right? Entire thing here. If you add all of this, then it will be in d dimensions. That is correct. The reconstructed data point is in d dimensions. Okay, try to tell you is what
Sir,
I
so
mean.
basically d dimensions means d points will be so
No, no,
there'll be d
no.
values separated by commas, but it's an m-dimensional subspace. Are
Right.
you
Okay, let me tell you this. This this data point here is how many dimensions? Say x1,
two?
2 dimensions, right? So if you project that data onto this, right? Correct. This is your
Yes, sir.
projection here. But this projection, let's say this is x1 tilde. Basically, it is not x1 tilde. X1 tilde will be this error plus the projection, right?
Right,
This x1 transpose w or u in this case. Let's say if you think about u, the what it is saying here, the line here saying the projected data point, right?
right.
The projected data point. And what is it? Which point he is talking about here? This one.
Yes, sir.
This is in n dimensional subspace. What about this? U is in one dimensional subspace, right?
Right.
So the data point which is x1, which was in R2, right, initially, correct? The
Yes.
projection of this, which will be in one dimensional subspace.
Okay, sir. So, sir, it will still be a point x comma y.
Yeah,
X
but
y,
yeah,
but it will be part of only a line. Like
line.
one.
Yeah, so all the point data points, right? Let's say this x2, this will, so all these data point which are lying onto this line, they
Right.
are actually coming into linear subspace,
Right.
right? So this line is a subspace in two dimensions, right?
Right.
So the sir is trying to say is that whatever the data points you projected onto, right,
Right.
that will be in
M dimensions.
yeah, basically m dimensional subspace, right?
Got it.
Now I
Got
think
it.
that's clear, right? Yeah.
Yes, sir.
Yeah.
Sir, last question, sir. What is reconstruction error, sir? What is the formula? Do we
Recon-
have to
yeah,
divide by n, or do we have to not divide by?
I don't remember exactly what you have to do. Maybe exact numerical I don't know. But the thing is, reconstruction error is this one basically. This one.
The norm.
Yeah. So you are just saying that this x1 transpose u1, right? Let's say u1 is
Right.
direction. Plus, if you add some error, that will give me the original data point.
Got it, sir. Got it.
So the reconstruction error is basically the all the error if you add, right, for all data points, that will be a
Yes, sir.
reconstruction error. I don't remember exactly what is the numerical. Maybe we'll discuss that tomorrow when I'll share that with you.
Sure, sir.
Huh? Okay.
Thank you, sir. Thank
Yeah,
you, sir.
thank you guys. Okay, thanks all of you. We'll meet again tomorrow then. Okay, yeah, bye bye.